Hi. So I'm François, and before I say anything else, I have to say something boring, which is that I have an employer, and my employer is not related in any way, shape, or form to that presentation. Any relationship you will make between my employer and this presentation will be entirely fortuitous and entirely yours to make. Any relationship you will make between this presentation and my day job will be entirely fortuitous and entirely yours to make. The idea being simply that this is a good old open source talk about how developers do open source, which is, in their free time, they're interested in open source technologies. 100% of that is open source, will be released on GitHub, and this is a personal presentation. Now, that we're past the boring stuff, I'd like to have an idea of who's in front of me. First, who was at the Scala meetup, when was it? 2 weeks ago by our excellent colleague Luc, about an introduction to Spark? Ah, 2 people, great. Okay, who's on the other end of the spectrum? Experience with Spark streaming, has it in production, and uses it on a daily basis? Nobody? Yes! Yeah, okay, good, perfect. Who's interested in, who has already is a little bit familiar with Spark? Cool. I have the perfect audience, it's great. Who's interested in Spark streaming? Uses it? Uses Spark streaming, a little bit less hands. Okay, cool. Fine. Now, Spark streaming is absolutely fantastic in that it's very, very close to Spark. So it's very nice if you like Spark already, but it's very nice for other reasons. Spark streaming is fun because when you deal with large big data, analytics, etc., you tend to have an interaction with the customer unless you work in a completely waterfall mode where you sell shrink wrap software, but there's not that many of those developers left in the world today. So you're going to come back to your customer, and your customer will look at what kind of analysis you've been doing. Your stakeholder will look at what kind of analysis you've been doing with their data, and they get more and more impatient. They want the results of your analysis not tomorrow morning at 9 in the form of a PDF report, but they want it in a dashboard. They want to access the dashboard 24/7, and they want the dashboard to update fast and fast. The other thing that you can observe perhaps is that when a customer comes back to you with more and more demands, it's because he's actually looking at the data. Those are the good customers. I mean, they report bugs, so they give you work. That's the bad part. But the good part is that they care about the data, they care about the work you produce, the insight you produce by analyzing their data. And what happens usually is that their understanding of their own business grows. As it grows, they start understanding what the patterns are. And because they start understanding what the patterns are, very quickly they want you to report on what is not the pattern. Is something happening with my business which is a little bit unusual? Now, if you're dealing with the industry, with mechanics, it's often something like predictive maintenance. If you're dealing with websites, it's something like anomaly detection or huge spikes and scalability in traffic. But the pattern stays the same. The idea is we want you to analyze the data fast. Now, there's many frameworks for in-memory data processing these days, in particular streaming. One interesting thing is that Apache Spark has a very, very interesting and simple model to understand the difference between batch and streaming. The moment you've been introduced to Spark, you've already been introduced to streaming, you just don't know about it yet. This is Spark in one slide. The idea is that you have a blob of data on the left, and that data is big. And Spark has a basic abstraction, which is the RDD, which allows you to address that data by distributing it across a cluster of machines. Now, this cluster of machines, executors in the Spark vocabulary, reflect the fact that data is hard to move. Often, the blob of data on the left is already distributed somewhere, already distributed on some kind of distributed file system, or ongoing distribution through some kind of data lake. which means that you're able to process this without having to move the data. In fact, Spark lets you program in function passing style. That's the fundamental abstraction. Is that instead of moving the data to your function being used to a single machine with a call stack, and you need to have that stack where you have the arguments and the program, etc., you are simply writing the function and moving it to the piece of data that it should act on. Now, this is Spark batch programs that we're all used to. Write one program, have it distributed on chunks of data, execute locally, retrieve the combined results of the local executions across your cluster. This is Spark streaming. The idea is that on the left, you have a time axis going from old on the top to new on the bottom. And that distribution operation we were talking about with executors, it's occurring on every clock tick as the data is flowing in through the wire. Fundamental abstraction of Spark streaming, you're receiving data through a server, through Twitter, through something, and the data keeps coming in. It never stops. As you have clock ticks that are marked on the good old wall clock, every clock tick signals that the data that has been received from until now, from the last tick, gets distributed on your executors exactly in the same form as an RDD. In fact, it is an RDD, the RDD for that particular batch. That micro-batching approach basically lets you reuse the kind of programming style that you see in the middle here. Spark streaming deals with the for each batch RDD, and then your advanced RDD algorithm that you've been writing for a batch job that maybe had nothing to do with this, or that one of your colleagues has been writing in a library operating on an RDD with statistic functions that you want to reuse, those are reusable and pluggable as is. The interesting thing is that that RDD algorithm will produce one result of the computation for each micro batch. Each micro batch operates on a micro batch execution of your algorithm operates on one RDD, and that RDD has a result, and that creates a stream of results as time flows on the right. One for each of the gray ticks that you have on the left. So far, programming model for Spark streaming, super simple. Okay. Now, you have, on top of that, an API which is made to simplify your life. Now, you are already used to map and flat map, and that's mostly the jobs for ETL. It means you have your stream coming in with data, but the data is not exactly in the form that your RDD algorithm is using. You'd like to produce an RDD on every batch, not changing the batch semantics, but with an RDD that contains something slightly different. Okay? So batch for batch, RDD for RDD, you're going to change it using functions that you already know about RDDs. Spark the API has transform that allows you to first get access to the time of an RDD, the batch time. You know those clock ticks. If you're interested in knowing which one that came with, it comes as one of the arguments to transform that is provided to you. But this lets you reuse a function that transforms an RDD and apply it on a D stream. The interesting thing here is that, again, you can make a function call to a function that is somewhere in the library that has been thought of from the get-go about batch. Nobody has thought of streaming previously, and yet you're able to reuse this code. Now, there's a couple of less interesting functions that are exactly homonymous to the ones in Spark, like LOM. We have map partitions that let you access to what particular data is distributed on a particular executor as a partition itself, and the reduce and fold that let you combine data as it comes on the wire. Wait, combine data as it comes on the wire. What does that exactly mean? Who here is familiar with fold? Okay, scan left. Scan left, we have two Scala users here. Okay. What would that give us? I'm going to reuse that. this is where I have to do some window switching, and where I realize that I may not be the best in the world at window switching. No, this is not the window I wanted to switch to. I wanted to switch to the other one. Hello. No, it's maximizing, but on the other screen. I hate technology, which is kind of annoying if you get an idea of my job, but okay. Yay! Okay. Yes, please. Okay. I have lost pointer. Should be able to do something like that. Okay, so if I have a scalar collection, 1, 2, 3. No, I don't have a scalar collection yet. No. Give me the pointer. 2, 3. Cell type. How do I change the cell type to key? Because
go to cell.
Yes, but I want to have access to the menu, and apparently without a pointer, this becomes very annoying. I mean, the pointer is here somewhere. It's flickering. It's just that I don't see it. Okay. I'm gonna do something else. Hello, you. Come back to Papa. Hello. Keyboard shortcut. Keyboard shortcuts tell me the cell type. I can do it. There we are. Back to business. Okay. So the sum so far is not exactly surprising. 1 plus 2 plus 3. I can also express that sum as a fold. This is still just scalar collections, okay? And with an operation that takes a pair and returns the sum. Okay, so that should be 6. Yay, can still count. Okay, now the idea here is that often you have an accumulator. You name this one accumulator to be very explicit. And the idea is the following. You have a collection. You want to operate over that collection in relationship with an accumulator. Here my accumulator is an integer supposed to represent the sum of the elements of the list. That accumulator is being updated on each element of the list from an initial value to a new value. I specify the initial value as the first element, 0, and I specify how to update it as you encounter a new element of the list as the second argument, the function that takes accumulator and y and tells me how to return the new value of the accumulator. Now, this so far, it doesn't sound very complicated. Well, it's just that you have access to it on an RDD. Now, if I have access to scanLeft, it's just the version of fold that returns the intermediate values of the operation of the accumulator as I am processing through the list. So far, so good. Yeah?
Is it possible to make the font a bit bigger?
Yes, it should be possible. You have to ask.
Thank you.
You have to ask the hard questions. It's very annoying. But also, please do take the time to annoy me, ask questions. Apparently, this has snapped with. Oh, okay. I understand why this guy is not happy with me. Say hello. Okay. So that brings me to reduce and fold. So already I can do something on a micro batch, which represents, let's say, the data that has arrived over the last few seconds, and do something that contains a little bit of state. This is the state within the batch of the elements of my list. So within the last 5 seconds. I can return something about the current batch, something like the sum, but if you really think in terms of sequential events arriving in your stream, for the duration of a batch, you still have a memory within the batch. You still know you still have extracted some data out of the previous elements of your stream. Okay? It's not a memory-less operation in the sense that if I have integers coming in over the wire, I double them. I know how to double an integer, whatever the previous elements of the stream were. Here, I don't know how to compute a sum for the current microbatch if I don't know what the previous element, as I look at one element, one integer, I don't know how to compute the sum over the last microbatch if I don't have the elements from the previous, that previously appeared in the same microbatch. So that reduce and fold are already abstractions that give me a tiny sliver of memory within the stream. Now, as you are all probably functional programmers, you know that stateless transformations are absolutely fantastic, very reliable. Everybody can use them. You can pass them around and have them return exactly what you expect without anything else corrupting anything. Now, this is functional, but if you consider it as an input-output operation that takes as an input your collection, and then yes, the rest of the world cannot influence you. And here we're in the same boundaries provided by the batching of the RDD. I just gave you an RDD which represents 5 seconds of data, and you have memory. You can do something within those 5 seconds, but you cannot see before those 5 seconds, and of course you cannot see after. Now this is problematic. This is problematic, and this is the solution. So the question is, okay, except sometimes in my dashboard, I am really, really interested in reflecting state. The disadvantage of the micro-batching model is that you can only receive and compute over data once the clock tick has passed, sadly. So if you have batches every 5 seconds, you cannot report on the changes in the world if you're if you're analyzing the logs of your website to see, for example, how many unique users are accessing your website at the moment. You cannot report any update until 5 seconds have passed. Then you can compute how many users were on your website over the next 5 seconds, compare them with the ones that previously were there, etc. And you can give that data away. Okay, now, if you want to output on your dashboard how many users there were over the hour of the day, hour number 1, from midnight to 1 a.m., etc., etc., you can simply have batches that look like 1 hour. Problem is, you don't get the answer until 1 a.m. plus a little bit to just compute whatever you had to compute given the data of the previous hour. So, we'll see that we'll see next that Spark streaming has abstraction for something called windowed streams, sliding streams. For those of you that are familiar with Spark streaming, don't jump on me right now. But one of the ideas that you can reuse to get more information about what occurred previously in the stream is simply update state by key. Now, update state by key is one of those functions in Spark streaming that has been operating over pairs. From a long MapReduce legacy, the designers of Spark have noticed that some things in Hadoop weren't bad at all. In particular, the insistence upon pairs, which reflect a heck of a lot of data that we're really interested in. Think of an identifier key joined with a payload of data. Now, sadly, the world says that you should always have some kind of counts of words somewhere on slide when you do a talk about big data. Sorry, it's below. So here's a count of words that have been coming in over the wire on your stream of data. Now, you're going to tell me I don't often have streams of words. Yes, but remember there's map and flat map. That stream of data coming in, that might have been a decomposition of the particular documents that and queries that your users may have been entering in your search engine. Yes, those are several words, but map and transform will let you transform those sentences in queries into words. You want to count them to search the words to find the words that are most searched for, or how many times each word has been searched for since you started your Spark Streaming app. This is how you do it. You have a stream of words. Each of them, you prepare them so that each of them becomes associated to a tuple, with the key being the word itself, and the count being 1, since the stream, the raw input stream of words represents queries as they come in. And then you use a function called update state by key. And update state by key is really easy. You can think of it as fold on steroids across batches. The idea is that you have a new value that comes in. Sorry, the arguments are inverted. The new values that comes in, that are the particular sequences of integers for the particular key that you are interested in, everything in there is under the assumption that everybody has the same key. So you're going to be given the new values, new counts, possibly pre-added along your batch, and a partial sum. If you have seen this work before, there is a good chance that you have been initializing an accumulator to some kind of value, okay? And that partial sum, originally 0, will let you update the sum to some new value, which will be the current sum if there was history for that particular word, and the sum of new values. This is the scalar collection, so I can just type dot sum and have the sum computed for me. Is it really clear what we're doing with update state by key? No. Good. Perfect. Because we're going to see it in detail. Now, update state by key is actually not completely intuitive, but the idea is that this can be maintained across your dstream state and across RDDs and boundaries. So first, to get an idea of what will be output, what do you think the output will be? So even better, what is the type of running sums? The type of running sums is a dstream. So it's a stream itself. What will be in that stream?
A map from string to integer?
You're going to have
a pair of string and integer.
Pairs of string and integers. The idea being that, and then this is a dstream with a map of string and integers, which means that you will see as many elements of, you will see an RDD of string and integer first, and then the idea will be that the map is implicit in the RDD. When Spark functions with pairs, the RDD itself makes sure that the values for the same keys are co-located in the right places in general. So this takes as an input this stream here. And this stream here is a dstream of string and integer. Okay? And with possibly repeated keys. A map of string and integer is fundamentally a collection of string and integer with the guarantee that the string is never repeated. That's what you'll get as an output. What you get as an output on each batch is the update to the current value of the current state. And you get a snapshot of the current state on every single batch. So if you have batch interval of 5 seconds, you get as an input all the queries that have been entered in your search engine over 5 seconds, transform them to add 1 to them and compute the sum easily, okay? And then you get as an output the current state of the sums for every single word entered in your batch engine, in your search engine, since the beginning of time. Isn't that useful? Suddenly you have values that you can update the dashboard with. Scrape the old values of the dashboard, replace them with the current snapshot of the state that tells you how many words have been, the count for each of the words that have been entered in your search engine since the beginning of time. But yeah.
One thing that's not clear to me is this works mostly for all the data that is coming in as time goes.
Yeah.
But you mentioned since the beginning of time, so that must
the beginning of your app, actually, when you launched your application.
Right. So, for example, if I have a ton of data that's been lying around over the past few years,
yeah.
Is there any way to merge my RDDs, my computation I would do on the RDD, and then merge that with the stream that's constantly coming in? Would there be any way to do that?
So this is the merge. You can actually update your state negatively. So that's the first very good instinct. What happens if a guy searches something stupid on my search engine, and then nobody ever searches that ever again? One very good example, if you're, which is maybe really important if you're somebody like eBay, is typos. Somebody does a typo. Now, if that typo is not done very often, the guy will not get any such results, but the typo may not be repeated for a long, long time. You're going to keep account for that typo, which is not super interesting to you unless you can figure out what the typo was and dereference it to what the user was really searching for, and you're going to keep that in your state forever and ever. That particular state here, it's okay, distributed across your executors and across your cluster, but it's continuously growing. You have counts for every word and every key and every word and every key, and the number of keys that get entered in your search engine, okay, it may not, after a while, you have most of the frequent queries, but the long tail is long, and it will grow indefinitely. You may not be interested in terms that are searched for once in a blue moon, but you can, this will get executed on every single key. What happens if you have a key that has not been updated during the last batch? So the idea is this: on the first batch, I search for house. In the second batch, I do not search for house. The key house will still get updated. What happens? What are the values of the arguments? So I search for house once, okay? Let's go through the first batch. I get house 1 as a first tuple. Update state by key goes through with new values used, which is the sequence of 1, okay? One element sequence with first element 1. Partial sum, well, it's none because I don't have a count for house so far. Current sum is partial sum get all 0, because partial sum is none. And I return current sum, which is 0, plus new values dot sum of the sequence of 1, which has only one element in, is 1, 1. Okay, I return sum 1. Second batch, no updates. And yet, Spark Streaming runs through that function for the key house. What are the possible arguments? Well, I know partial sum because I just returned it. It's sum 1. What do I have for new values? For new values, I have nothing. Okay, which means that in my particular case, this is actually somewhat not very good, to be polite. Oh, new values that sum does something. No, okay, okay. New values that sum will return 0 on an empty list, and the current sum will be 1. Okay. After the call to get or else. So I'm going to return 1 and update the state for house. Is that good? Maybe not, right? I'm preserving that state for house forever and ever. So this is the fundamental idea of this talk. We're going to beat Flink at their own game just because we have noticed that. In fact, the Spark developers have noticed that and have thought of, oh, okay, in 1.6 we're going to make that situation a little bit better. And when I say beat Flink at their own game, I mean that we're going to have even time processing and that we're going to hack it within fast. That's the idea. So Spark streaming also has something called tumbling windows and sliding windows. Ideas, this is an aside, by the way. Just to motivate that even time is actually interesting. The idea about tumbling windows and sliding windows is all here on one side. Okay, you have elements that are small squares. Elements have colors. The colors are unified for the batch in which they arrive in. In fact, the batch in which they arrive in are in gray above on the first line. Now on the second line, you have the option of doing windows. So if I have D stream on top with those colored elements and 5 seconds of batch processing, what I have here is the call to window 10 seconds on the second line. The idea is that you can just unify those elements as if they were coming to the same batch. This is what I told you about. If you wanted to give an update just every 10 seconds instead of 5. If you were wanting to give an update every hour, you would call window with the argument 3600, because there's 3600 seconds inside it now. Okay, Windows, simple, changing how Windows work. Now the third thing, the third line, is a call to a sliding window. Here I want a larger window than the original batch I had, but I want it to reflect not the last hour or the last 10 seconds, but I actually want to reflect the last 10 seconds every 5 seconds. So every 5 seconds, I want the elements that have arrived over the last 10 seconds. Okay, so it's equal to window 10,5 with a slide, which is equivalent to one batch. Okay, so here I have batch 1 and 2, and here I have batch 2 and 3, instead of having 2 and 4. Now, those functionalities are in here in Spark Streaming as is, but there has been a lot of commentaries and a lot of punching against Spark Streaming. I mean, if you are interested in details about S4 SAMSA, will Apache Flink, I'm happy to give all the details to you, but the goal here is not to make a fight of frameworks, is to say, hey, okay, there's 2 things that we want to look at with Spark Streaming and that we can't figure out, and it's when you have out-of-order events and when you have no particular batch interval that makes sense. The fundamental of micro-batching in Spark Streaming is, okay, you're going to chunk your data coming in over the wire by a fixed clock tick. You have to choose this clock tick. If you want updates every hour about counts on a website, that's okay, that's fine. You can show the number of distinct users. But what if you want to really analyze the content of a user's session and you don't really know when a user session will finish? You have engaged users on your website that have long sessions if you have a retail website. They enter their details, they are new users, they create an account, the transition graph on your website is horrendous, and the guy is there for 1 hour. Actually, it's your job to make sure that he's there for less than 1 hour. But you actually want to analyze how much time they take. It's extremely important. And then you have users that bounce. They came to your website through one advertisement. The advertisement where the click was completely intentional. They see that they're on a retail website. They say, yeah, okay, I was reading my newspaper here, and they close it down. What is the batch interval that makes sense? And the answer is none of them. There are ad hoc facilities in many of the existing frameworks. There's everything you need to build that for yourself in about 20 minutes with Spark Streaming. So that was my sliding slide. And we get to map with state. But before that, I'd like to get to, yes, testing all of this. Okay, so let's play with a notebook and have an idea of what happens if I start Spark Streaming. The notebook, the Spark notebook at the moment is not happy with stateful streams, so you might see annotations that are absolutely not relevant to you and that are here because of the notebook. Look, we need to have a discussion about this one. Label does not maintain the Spark notebook, but it would help if they need a Scala guide to tell them about closure. Anyway, there's a bunch of things that you're not interested in, but so the stateful streams in Spark Streaming, this is not exactly the subject of what I want to show you, but every stateful stream has a dependency on what happened previously in the stream, right? For fault runs, if Spark Streaming happens to die and have executors dying, etc., it needs to be able to recompute what the data that was being computed on, your update state by key, your current update of the count of words that you've been seeing from the beginning of time, it needs to recompute this. But the problem is that to recompute this recurrently, you would need to have access to the D stream since the beginning of time. Recompute since your app started. Now, in order to avoid that, you need to activate something in Spark called checkpointing. And if you try to update the function without thinking to use update state by key without using checkpointing, Spark will output an error and remind you precisely with a good error message, hi, you need to use checkpointing if you're using that function. Okay, so that's what I'm doing right here. Checkpointing represents Spark Streaming serializing the current state every 10 batches or so. Okay. And it seems that, okay, now this is new in 1.6. I can generate random RDDs that contain arbitrary information. That's quite interesting. I'd like to test those random RDDs, please, to have an idea of how good that normal distribution random number generation can be a little bit fiddly. If you've been following the crypto world these days, you can get people that tell you that they're really they're generating random numbers and then not so much. So here in 1.6, I have access to a random LDD, which means that if I get a Spark context, I can generate a random LDD with a normal distribution. Normal distribution for the statisticians among you in that particular case means with a mean of 0 and a standard deviation of 1. And I want 100,000 elements in there, and I want this distributed over 10 partitions because I have 8 cores on my machine. Okay. So this is a function that will generate a random LDD. Cool. Now, if I want to look at the content of that RDD, I can even take 5. Ta-da. Oh, I get numbers and they look nice. I mean, by that, I mean that they look like if they've been randomly generated with a mean of 0. They're relatively close to that mean. There's a central limit theorem that tells me that eventually, if I compute the mean over a large number of samples, I should really get 0. We'll test that. And then they should have a standard deviation of 1. So again, they're not that far from it. Okay, cool. I like to have an idea of what the distribution looks like. Ha! Here I'm creating a stream out of that random RDD generation. So here is one fantastic testing facility that has been in Spark Streaming since forever, and that I've been abusing and using ever since the discovery was there, and sadly this was not since forever. I wish I knew. But you can have a mutable queue in Scala, and as long as you're adding stuff, a queue of, it needs to be a queue of RDDs, but as long as you're able to add RDDs to that queue mutably in the memory, the Spark Streaming is going to task itself with operating on it as if it was a D stream. That's absolutely fantastic. Okay, note that so far I have created the queue, but I haven't really done, you don't need the transit annotation. This is due to my usage of the Spark notebook and a reported worked on bug. The second, I haven't added elements so far. I just created a function that let me generate random RDBs. Okay, this is purely a hack about the Spark notebook, sorry, but it gives me this widget. I have that widget, and when I call apply on that widget, I will be able to display stuff on my notebook. Hi. Okay, to make sure that I'm not stealing away from you and embezzling you, I can update my notebook here. Cool. Cool list. Okay, that's the whole gist of it, the Spark notebook hacking. Nothing to do with Spark streaming. Now, if I want to compute a running sum, oh wait, I'm going to enter into my queue for each batch, each 5 seconds. Well, why 5 seconds? Because this is how I've created my Spark streaming context with seconds 5 as an argument. Okay, so batches every 5 seconds. And then every 5 seconds, I'm going to receive a new RDD because, I mean, I've never entered anything into that queue, but you can imagine that in the end, I'm going to start pushing RDDs there, okay? So I'm going to have an RDD of randomly generated doubles, okay? And I'm running a small statistics exercise here. I'm transforming those doubles so that I print them to a string. Now my double is a word, hi. And then I'm grouping them to have several counts by the second decimal of that double. So I have a double like 0.8567, and the string that I'm mapping them to is 0.85, okay? And I say that I've found this number once. And then I run the partial sum function that you've been used to and that you now completely understand through and through. And then running sums is a distream itself that reflects the sum of how many elements I've been seeing about this one so far, about this particular word so far. My word happens to be a number, but no influence. What's interesting here is that I want to materialize it, okay? So it's a distream, it contains RDDs, and each RDD contains the string mapped to the integer of how many times I've seen a number that started with the same 2 decimals, okay? I would like to know, first, what is the size of those numbers? As this is the size of all numbers that I see, all the keys, okay? We notice I'm always updating my state. So this number is going to be constantly growing and growing and growing, okay? Now, I look at the elements that I have somewhere, that I have in my RDD, and I collect them, which lets me operate on them as a scalar collection. Don't do this at home, this is a test. If you collect really big data out of your distributed cluster and into one single machine, that single machine is going to die. Okay, but here the collect, I know that I have 100,000 elements being generated per RDD. Out of that, I compute a state, but the state should not be too gigantic. How many distinct elements in the end should I see? How many possible keys do I have, roughly? So I'm going to have numbers close to 0, but potentially...
If you wait long enough, it can be pretty big.
Is there a limit?
No.
No limit?
I mean, like 200?
We have somebody that's on the track there. First, there's a limit, there's a bound.
Yeah, that's the boundary of the representation.
It's a string, okay? It's a string with 2 decimals. Now, it's true that if you really generate random numbers, purely random numbers, and if you wait until infinity, then you might have a problem. Why? Because, yes, once in a blue moon, so if you know your central limit theorem, you'll know that as you generate really random numbers, the probability that they are further than 5 sigmas, 5 ones, so larger than 5 in common terms, than the mean, so 5 sigmas away from the mean being 0 and sigma being 1, that means larger than 5, is less than 5%. There's a Chebyshev bound somewhere, a math theorem that tells you that. But ultimately, if you look at small enough probabilities, you could get any number, arbitrarily large. But you will get them with a probability which is very, very low. And anyway, this is a demonstration. I'm going to feed a number of RDDs to my D stream, which will be finite. So we're not going to wait until the universe freezes over. So we're going to get numbers that are close to 0, mostly 1 digit away from 0. Okay, because if you want to be larger than 10, you have a chance which is like astronomically. If you do your number, the probability that any number you get with 2 decimals is larger than 10 gets quickly astronomically small. That's a property of the normal distribution. But true enough, if Spark has a bug and they are not generating those numbers randomly according to the normal distribution that we're expecting mathematically with all those bounds and all this math that tells me what to expect, yes, I could be meeting the bound. But having tested that, it works relatively nicely. What I get are mostly numbers that are smaller than 10. We'll actually see the least sin number. And the least sin number, if that distribution is really normal, should be far away from the mean, because those numbers have a lesser probability. So it's going to be either a big number, larger than 0, think 5, or a very small number, think -5. Okay? The most sin will probably be very, very close to 0. There's a good chance that it could be 0 as well. Again, probabilities of a normal distribution. The mean, well, it's the mean of how many times I see each number. How many times I see each number depends on the number of batches you send in, of course, because you are sending 100,000 numbers every time. But it also has the probability on the distribution of how many distinct elements you could get. How many distinct elements you could get is roughly, since this is going to be less than 5, you have a 9 for the first digit and then 2 other digits. Okay, 9, 9, 9. I'm going to get roughly 1,000 numbers if I wait long enough. And then if you work out the math, the mean that you're going to get is going to be roughly 100 times your number of batches. But let's see if those instincts are okay. What I'm doing here is collecting elements, computing interesting summary statistics, sum, mean, least sin number, most sin number, and then I'm displaying them using my super duper list update that I have above on the notebook. Now what's interesting about that is that it lets me update my display on HTML above completely seamlessly as I progress to my stream. And then I'm starting my Spark context. But wait, there's nothing in my stream yet. Not a problem. Spark can generate empty RDDs, so the first RDD is going to be empty. Okay, and then I can push some RDDs. Lines was my queue, and then U was my function that was generating a random RDD. Okay, let's push some. And then let's wait a little bit and pray that the demo gods are not too bad with me. Oh, I've already seen 714 elements. Sum of elements 300,000, mean 300, and it's still growing. The least sin, as expected, is quite far away from the mean of 0, and the most sin, as expected, is quite close to 0. My size should not go above 1,000, and the sum should go to, I'm pushing 30 batches. If you've seen my loop, that is for 1 to 30 batches of 100,000 each, so I should go to 3 million if I'm not screwing up things completely. And the mean should go up to 3,000. Let's look at this. to see how many batches we have left. 18 batches. It's a scandal. It's way too long. We don't have that kind of time. Okay, you're gonna have to trust me. It is still growing, and it will eventually reach a size. You see that the speed at which the size grows, though, gets less and less. The size is the total number of absolute keys that we've seen, okay? And the rate at which it grows is less and less because most of the elements that we've seen so far were already in the map, in the state. Now, the problem with that growth is that you can have the impression, if you run your Spark streaming job for like 1 hour, that this will not grow indefinitely. But believe me, users are weird. And in particular, if you run a search engine, there's not only users, you also have spiders, crawlers, script kiddies, and people trying to spam your search engine, hoping that somebody is looking at the dashboard and looking for Viagra. Some people try to game search engine results. Some people try to give you the impression that there's a boost of searches in this or that particular political candidate which is running for the US election at the moment. Because people, including journalists, write papers on the Google search trends. So this number might grow indefinitely if you have a script that is inputting shit in the middle of what you're doing. You might also see very, very large counts. So the fact that I'm counting this with 32-bit integers, if I have a script that is trying to make, I don't know, who's the minority candidate that's not in the race anymore. Marco Rubio is not in the race anymore. If that tries to make Marco Rubio popular, I might see counts that go way above 32, what is representable by a 32-bit integer. The sad problem of interfacing with real users. You have to think of everything and be really paranoid. Okay, so we have reached 3 million. We have a mean which is around 3,000. We have seen nearly 1,000 elements, but not quite. We have a least seen number which is far from the mean, most seen quite close to the mean. Okay, this is a decent normal distribution.
I missed something. Why is the mean 3,000 and not around 0?
No, this is the mean of the number of times you see an element, not the mean of the value of the elements.
Right.
Okay. Okay, so, and this is quite equally regarded because if you look at 100 and you multiply it by 3,000, you should get something that is close to the sum. So we have not been losing elements. Now, if we look at this, my job is still running, okay? Console messages in there that show me that the job is still running, and I actually need to stop it if I want to do something serious with this. Okay, so far so good. We have seen how to do something with Spark streaming with state. Now, we are going to see something. Ha! Is that going to work? Yes, maybe with this. I might have to restart this guy, which might. Who's this guy? Doing what I expect it to do. Is that still running? No, it's not running. Come on. Oh my god, it's still running. Okay. I need to restart it. Ah. Yeah, I don't have access to my pointer on the auxiliary. Yes. This is very annoying. Okay, now we're going to look at track state by key. And track state by key is way more interesting. Track state by key lets me do that kind of update without looking at every single key in my state. You're just updating the keys that have a new value encountered within the last batch. Now, if your updates are sparse, which is often the case if you're looking at search engine updates, this is incredibly useful. You may have 200,000, the size of a dictionary basically, words that are searched for in your search engine, and then on every update you need to go through those 200,000 words and update some state there. You're not going to update any state, any count for most of those words. For most of those words, you're just returning the state as is. Track state by key is the implementation by Spark Streaming available in 1.6 and future that lets you update elements only if they have one new update. But then the question of my excellent colleague in the blue sweatshirt there is, what do you do with state? What do you do with the previous words that have been entered by guys on my search engine? Do they stay here indefinitely? Turns out you have the opportunity, if you look closely, to do something that only that Flink is planning to do in the next release, which is solving the problem of user sessions. So the answer to what can you do with state is you can time it out. You have an inner tracking of when that guy was last updated, and Spark lets you remove state that is too old. When should you use update state? When should you use track by state? You should, track state by key, or which has been, have been in the development mode of this. Track state by key has been renamed to map with state. It will be displayed here as map with state. I have updated the slides. I have not updated my head. This will come very shortly. Map with state. Map with state is an API that requires you to define all those complex things, which are the state, and then do a call which passes the complex state spec that we've seen on the previous slide to map with state on a district. And then you get, let's see what you get. This is what you do if you have no sense of batch that helps you determine what a user session looks like. I don't know what a user session looks like, but a user session looks like something that has been updated by the recent actions of the user, unless there has been a gap larger than a certain time. If the user hasn't been updating anything on my website within the last 10 minutes, the first 15 minutes, the first rule of thumb is to think that, hey, he's gone. Okay. Anyway, if your website is correctly coded, you already have that kind of notion of session state timeout in the website itself, so that the user cannot basically do a denial of service on your website by starting new and new user sessions with new cookies, new browsers every time. Any script can do that. So let's reflect that in the model. You want to compute something on your user. You want to understand if that user is liable to be buying a lot in the next few minutes, and therefore you should really, really send him a customer representative, personalized ads, and be horrible to him, or if he's just browsing and you should tease him very slowly, perhaps a book recommendation here, perhaps something else, but he's not buying yet. Okay. You have a stream of user actions coming in. What do you need to develop to update what will be fundamentally a fold? You need to understand which state you're going to update, what it represents, and you need to update it. So you have as an input the state for that particular user, an initial state possibly, if you have never seen that user. It's somewhere in the arguments to that function. And somewhere in that function, you have a call to state_data.update with an updated session. So the question is, what's in my state? Well, a user session in that case, which is my own self-defined type, could be anything. And in the end, I create a new session, a new value of type updated user session, and I call state update. So far, so good. But wait, why do I call state update rather than returning the new value of the accumulator the way I was doing it with update state by key? Well, that's because you don't return the same thing. There's a return explicitly here. It's not very idiomatic for Scala users, of course. The last value the last expression that is being computed in your function is what your function is going to return. You all know that, but it's there to be very, very clear about the fact that I'm returning something, and it's not the state. I'm returning a user model. Track with state returns something that is what you want. Remember the old dstream with update state by key? We had all the counts, possibly a large object, all the counts for all the words that we had encountered until the beginning of time being output on every single batch. Not really useful. Here, you can return exactly what you want, which may be the updated user model, because that user, depending on his previous actions, has just done something interesting that lets you determine if he's a strong buyer, an immediate impulse buyer, or not. That's what you need to act on. If you're doing anomaly detection, suddenly you're tracking the state of 200 machines to see if one will break down. This will just let you report the one that is going to break down, as opposed to all the machines you're dealing with the state of. Okay? So, as an argument, I get the user ID. Remember, all of this is indexed by key, so this is really the user for which I'm tracking state. So this is the key I'm interested in. And I have the new data, which is the new data coming in on the stream. So that means that the state update function will be usable on a D stream of user ID, first element of the tuple, user action, second element of the tuple, payload of my D stream. Okay? I take the current session, which is a call to get on the state data. There's a get option here. There's I let you consult the Spark API or see the demo to figure out what this returns. You compute your updated session based on the current session and the new data you've received from the user, and you update your session. So far, so good. But as a side effect, you can also update a user model and return the particular user model. You can even return it in the particular cases where you are interested in that and return an option. Return none for the guys that you're not interested in. How you use that stream of user actions? You pass it the state spec function, state update function. You can build a state spec with a little bit more data, and that's often useful for a website. So state spec dot function, meaning here, this is Spark Lingua for if you are used to updating SparkConf, you know that you can do SparkConf dot set my option 1, dot set my option 2, dot set my option 3. They have functions like this that update different arguments of one function. If you want to build the state spec as one function call, you can do it as well. So we'll see in the demo in 1 minute how you do that, because I really don't like that particular style, but that's a question of style and choice. You can update that with a timeout. If I haven't seen my user for 10 minutes, destroy its state. So suddenly, the state you have for your website is now growing indefinitely in memory, and you're not killing your cluster because you are registering the state for all users since you've been starting your application. And now the problem you have is, what if I want to do debug, diagnosis? My application is not returning exactly what it should. I want to also return to a logger the user sessions that I've been seeing for that particular user, organized in the form of my special type user session. I would want, in fact, the return values for update state by key. And in that case, I just call snapshot stream. Snapshot stream will give you exactly the return of the state. So let's see that in action. Setting up my Spark streaming contest, actually. No kernel, he says. Yes, I want to reload this site, please. Hello. This should become ready soon. It's there. So I have a function that generates RDDs. If I look at 3 of them, I still have an RDD of double. And here I'm going to do the. I'm still generating my queue of RDDs. This is a purely pure maintenance on the notebook so that I can display that cool list. And here I'm going to do something weird. I'm going to do something that at the moment only Flink purports to be able to do. I'm going to do event time processing, which is the other problem that we have in Spark Streaming along with users. Now, the doc and the examples that we've seen, those examples are actually provided by Databricks as the canonical example of map with state. Here we're going to use map with state to solve the other weak point of Spark Streaming, which is how do you do event time processing? You have events that come every clock tick, but they come with an event time processing within, an event time specified within them, which is the time at which an event was generated. But because you have delays in your network, because you may lose a connection for a while, because your Kafka server has lagged, or maybe doing replay or something else, those timestamp events come in, but they come in late. Or they come in early from your point of view. They might, if you are expecting a certain latency, so you are computing that, yeah, okay, I'll get the events 2 minutes after they arrive, and then suddenly you have no congestion on the network, and some sysadmin somewhere has been replacing that 10 megabytes line but by a gigabyte line, and suddenly everything is faster. So you would like to create a stream that creates a time which has been delayed by a random number of seconds, actually a random number of seconds which is going to be a proportion of a batch interval, which is going to be dictated by whichever random number I'm receiving. So I receive random numbers that have a standard deviation of 1 that are mostly going to be between -1 and +1, and I can use that delay on the time of the batch to simulate event time processing that might be roughly up to 4 batches before or 4 batches after what I'm doing. Okay. This is the function that creates my delayed stream by applying transform I've told you that if you're interested in transform, if you are interested in timing the batches that are coming in, you should be interested in transform. So here I use a transform function that takes my RDD, takes the time, and which will be the time of the particular batch at which the wall clock at which this event arrives, and then delays that by up to 5,000 milliseconds, meaning one batch interval, in either direction. And suddenly I find a T stream of time, which is my event time, and then the double that I've still kept as a payload. And then I format my stream a little bit here to make sure that I transform the double, which was a payload, into a key, which is exactly what I've done before, which is the double itself up to 2 decimals. Okay, so 0.561, okay, will arrive at the batch time, the normal batch time, minus 0.561 times 5,000 milliseconds. So it's been delayed by half a batch. Okay, and the payload will be 0.56 because that's the string 0.56 because that's 2 numbers after that. And here I'm creating a circular buffer, which is basically a vector that can contain up to 4 elements, and if you had a 5th element, it drops the old one. It's a pattern that was called enrich my library these days, because
you're correct.
Yes, political correctness. And I'm here implementing in about 12, 15, how many is that? 3, 6, in about 20 lines, maximum 25, at least one slide, I'm implemented the struct state func, which will return a D stream, whichever counts. So here, what am I doing? I'm following the state spec from Spark. I'm creating state fun that takes the time of the current RDD that comes in, and the key, which will be the string I encounter. I take the value, which will be the event time at which that element was generated, and a state which contains 4 time to int associations. Now, what is the interesting thing in my circular buffer time to int? It's because I'm going to use it as a watermark of how far behind the elements can possibly arrive. This notion of watermark is also used in Flink, and the idea is this: you cannot keep state forever and hoping to face any lateness arbitrarily long in the event time at which your events arrive. You can only bound it. And my bound here is 4 batches. What I would like to update as state is how many times I have seen my key, here the integers, for each particular batch interval, and my batch intervals are the particular windows in which I associate that particular count. So an event comes in, so I have 4 counters for the last 4 batches, and if an event comes in telling me, hi, my event time is within the last batch, I update the counter for the last batch. If it tells me, hi, my event time is within the last batch -1, so within the batch before, I update the counter for the batch before. Hi, I'm an event time, you have seen this number for 2 batches ago. I update the counter for 2 batches ago. Hi, I've seen the counter for 3 batches ago. Update the counter for 3 batches ago. 4 batches ago, shouldn't lead to an update. If you have an event that is in the future, I decide here to not have it be part of an update. So what I'm basically doing here is that I call state only if, so I have a little bit of arithmetic to figure out, to compare the batches of the event time of the arrival value of my object and the batch time of the real legal batch time at which the wall clock at which I'm supposed to receive events. So everybody is supposed to be in there. If there's no lateness, no events that arrive forward, everybody is supposed to be in the condition where this is equal. Those are equal. Here I have a little bit of Scala that basically takes the current state, the current counters for that particular key, that particular number. I take the current counters and split them between the batches that are strictly before the one that I'm considering. The one I'm considering is still not more recent than the official wall clock, right? If it's more recent than the official wall clock, we fall in that case, and I'm not updating it. I'm not updating anything. There's no call to state update in here. So I take the ones that are before, and then I look at the ones that are here or after. If there's no event after, it means that I have never encountered a batch, and never encountered an event for the current batch, in which case I update the counter with the time value of the first event that I've encountered, which is the one I'm treating at the moment. If I have already seen this one, I have a count for it. If the batches are equal, so I update that count. If I have if there is, I have not seen a batch, an event for that particular batch, but I've seen something after, then I add this counter for the beginning of it, at the beginning of those. Which means that at most I have my data structure ensures this add item here, where I basically stick together before and after. This guarantees that I'm constantly updating my counters, and as soon as I have more than 4 batches, there's one that drops, and that is being dropped by the data structure above. And I update with my new state. Now the interesting part is that in that case, I have 4 counters per key. okay? Up to 4 counters per key. Is that what I really want to display an update? In most cases, no. In most cases, I'm just interested in updating the new counter that has been interesting for that particular key. So what I'm doing is I find wherever I have added that update, because I know that I have added the update for T somewhere in among my 4 batches, and in that case, I report, oh, by the way, for that key and that particular timestamp, the new counter is this. And that's what I return. Now, the interesting part of it is that I can call that, have fun with having 2 partitions for the updates of the returns of the count. The initial state is just what initial state you should have for something that doesn't have counters initialized so far. In which case, mtrdd, I don't start with words that I've already seen. Now, this is fun if you stop your Spark application and want it to pick up from some serialized state. That might be useful. And I time out after 40 seconds. Why? Because I have tested the normal distribution before that in the update state by key, and I've seen that at most the largest number I see is around 4. Now, the largest number I see is around 4. That means that the event time of my elements are delayed by at most 4 batch times. So with my batch time being 5 seconds, I am 4 times 5 seconds before or after, which means that if I really want to be sure that I'm going to delete state for things that have not been updated for a long time, 5 seconds times 4 is 20 seconds. Before or after times 2 equals 40. Even though I'm not keeping state for after. That's because I have not missing typer on the clip. Okay, let me simplify this by just suppressing that code. We work just as well before that. We won't have the append. Yeah, it's done. We'll just have the count update. So I do a map with state, and in the case of my count updates here, for HRDD, I report the new updates. And logically, if the demo gods are here, I'm doing event time processing. Event time, here I report the updates, but notice that not all the updates are within the last batch. Now, statistically speaking, the updates that we are going to see are probably going to be either within the last batch or within 1 batch of that, the previous one, which is why we see 2 numbers, and we see 2 numbers for the consecutive updates for which I really receive new values. And we see those numbers increasing for zeros, so 64, 65, 66, which tells me that, hey, one cool thing about this, the amount of flag that Spark Streaming is receiving for not giving you enough data or giving it to you with a high latency because you have that micro-batching model which does not let you see the conclusions of the computation until you are finished computing on the current batch, well, that's wrong. Hi guys, I'm updating counts as they come. Okay, I'm processing the previous batch, yes, but I'm not adding latency until I am finished processing and finished doing additions. You can get the updates as they are coming in. Okay? Okay, super quick sentence on structured streaming. Structured streaming is absolutely awesome. You should want to read blogs, get into the discussion, and possibly get into this discussion with the developers on Jira. They are extremely attentive to this. The idea of structured streaming is to reuse the data frame engine, which lets you at the moment optimize queries and output them as an execution plan to your executor and update it. And to reuse that to let you do this on infinite data frames. So you have an infinite data frame that is, if you think of it as a SQL or actually NoSQL, table, something that constantly gets new rows added to it as they come in over the wire. Your computations, all of them have an API that is incremental, meaning a new row doesn't trigger the recomputation of all the data since the beginning of the universe. All of this is based on primitives that are as simple as the ones that we already have on RDDs. And one very, very cool thing that is very fledgling at the moment, which is why you should get involved in the computation and present your use cases, is dynamic queries. You'll be able, on those infinite data frames, to change the query that you're doing as your Spark streaming application is running, not by changing your notebook, creating a new notebook, and relaunching your Spark context. You will be able to do it live as your application runs, which means that suddenly, if you want to see what is changing in your patterns, if you want to analyze your data, it's available to you right now. There's no latency. Okay, big tour of how to deal with state in Spark streaming. I hope you have retained, in conclusion, of course, all those notebooks and slides will be made available on the internet. Personal talk, I can do whatever I want, it's so cool. Those will be on the internet. I hope I've convinced you of two things. First, event time processing is not impossible in Spark streaming. It's 20 lines, okay. It's a bit more complex than having a primitive for it, but it's not impossible. User sessionization, track read state, it's done with insanely better performance. We still have one slide that says that. By the way, hi, track read state, okay, you can do a little bit late and update state by key. If you really need to update every element of your state, whether it has new values or not, on every batch, you have to use update state by key. You don't have a choice. Most people don't care about state that hasn't been updated since ages. Then you can use track state. You can use map with state, in which case you get much, much, much better performance. Okay. User sessionization, possible. Event time processing, possible. Structured streaming, get in there, read the blocks in advance, try to talk with the Spark developers and present a use case for which dynamic queries wouldn't work. We are super interested. Thank you very much.
Thank you, François. That was kind of mind-blowing and a bit dangerous for other things to try. Do you have any question?
In production, how do you deal with states when you do an upgrade of your application?
Aha! This guy likes to only ask the difficult questions. Yes, this is problematic. So data sets and structural stream have options for inferring. So if you are in the data frames world, everything is easier. If you are in the data frames world, there are options for inferring schema and inferring schema from serialized state and inferring it from serialized state that may or may not contain the particular field you've been adding. Okay, Spark streaming also has in data frames the dealing. You can deal very, very well with absent values for data, rows for which you don't have data. You can filter them. You can precise in your computation. Basically, it amounts to in every function, every UDF that you define on the data frame. We were used as functional programmers with dealing with the base case of the recursion. Here you have one more base case to deal with, which is the absence of data. So the story for data frames is nice. The story for RDDs, not so nice. You kind of have to take it into account in your data. I know it's painful. The idea is to push as much data processing as possible to the data frames world because you get performance for free. Now, updates of a Spark streaming data format as your application is running. Yes, okay. This one is going to be a little bit difficult, but because Catalyst is running on every single iteration, you can actually have something that benefits somewhat from the schema inference. I would be interested in that, in seeing that. Actually, you are now tasked, Philip, with Yes, I know where you live. Knowing the structured streaming, annotating the structured streaming design doc with, hey, by the way, you're doing other queries, would be nice if it could take into account data format updates as the application is running. If you can relaunch your application, okay. In the data frames world, everything is set for that. In the RDD world, a little bit of code to write by hand. If you are updating another query with new data, yeah, okay. This is the kind of questions I like. I'm going to be reporting things. Hey, I thought of something brilliant. Yeah. Thanks.
I have a question. So we have the streaming, Spark streaming, okay, which is processing data and maybe make some process, save it somewhere on your in whatever format. And then you also want to have a play application who render those data. What's the best way to have the play or REST code for my play application that goes there? Is it WebSocket? Is it how do you make these things communicate?
So
which direction?
I'm deep in
Sorry?
the back.
Which direction are you asking?
The reusing.
I make a REST code and I want to see whatever information that you are displaying now, but I also want the Spark streaming process to go its way.
Yeah, so basically having a server that continuously gives you access to the results of your computation and lets you display it to a web app, to a dashboard, etc. I'm deep inside the backend guy, so I cannot really speak from personal experience, but I talk regularly to people that constantly have that problems, and I've seen three particular patterns. Either the guys that go to Cassandra, saying that, well, we have the CRUD model of development that has been changed to create an append only. And Cassandra is kind of modelizing that very nicely. And you can have handmade code that calls Cassandra and returns exactly what you want. Fine, fair enough. That's usually the basic answer with which everybody is happy. Cassandra distributed database, you can co-locate it with Spark Streaming so that it can even be a layer that serves as an intermediate between two Spark Streaming applications. Spark Streaming application feeding data into Cassandra, and then another Spark Streaming application that feeds itself from Cassandra and from another data structure. They have a Cassandra Streaming API that can let you read data as they are being updated. Very nice solution there. That works until you are really you are really completely unable to predict what the queries are going to be made against your data. So it's not the case of a website or a dashboard, but it's really a special dashboard in which you let users enter queries. And that opens a gigantic Pandora's box, right? Because suddenly, or BI tools that let you enter queries. Suddenly those guys want aggregations over 1 hour, 2 hours. Nice websites are nice, right? Dashboards are nice. You kind of have plans for the user interaction. You can toggle a few things, change a few colors, a few ranges here and there, but you have planned for that in advance. Suddenly you open the door to the BI guys and it's a nightmare. Suddenly that leads to queries on your cluster. It's an absolute horror. Usually what those guys want, though, is different aggregations on different days, different kinds of queries. Eventually, that will be in the dynamic query engine of Spark Streaming. In the meantime, what people want to do is use approximation techniques to reflect that all data might become stale, and that if you want quick sums over aggregations of some batches that are going to change all the time, the database engine should actually take that into account for you. And there are two open source projects that actually tackle that problem head on, which is they are database engines that have been thought of with the idea that they would receive data streaming and that they would receive queries over an arbitrary length of the stream that the computation has been working on. And those two projects are Druid, Druid.io, and PhiloDB by the topology guys. and they have done something very nice. Tweet is really, really amazingly good on counters and on arbitrary time aggregations with an arbitrary precision.
Cool. Any more questions?
So, just one small question. You talk about data frame, but all the stream API is based on RDD. So does it make sense to use data frame in the context of?
So, all the streaming API is the streaming API. So if you look in a place which is the dstream is a data structure defined with RDDs indexed by a microbatch, of course you're going to see here the functions that refer to an RDD. So far, you can create data frames arbitrarily for any RDD at a cost that has become less and less taxing over time, so that you can use the data frame API within your RDD boundary, right? You can use your RDD, your data frame API in a call to map with state and have the data frame or the data set. This new API that came with 1.6 as well, be updated within something like map with state. The whole point of structured streaming is to give you a real data frame API, not something that requires you to twist your data frame creation so that it doesn't cost too much and then call on something that is really a data frame.
So right now, does it make sense to use data frame without this new structure stream?
Well, if in streaming, yeah, it's a bit complex because you might have a cost of.
Yeah.
It depends on which latencies you're talking about. Catalyst is well implemented. So relatively high latencies on the order of minutes, no problem there. I've seen personally problems occurring, but the problems that occur on the order of latencies on the order of seconds. You pay the data frame cost creation once. Honestly, for having been acquainted with the code of a number of people, data frames are much harder to shoot yourself in the foot with. So if you work with people that really understand Spark through and through, maybe not. Maybe data frames so far until structured streaming arrives don't make sense. If you work at low latencies, seconds, okay, not yet. Wait for structured streaming, but have a look at the design docs, comments. Try to envision what your usage could be. If, on the other hand, you work with people that might not be super familiar with Spark streaming or relatively high latencies, yeah, they'll add a field to your dashboard in much more reliable fashion and in a fashion that will not wake you up at 2 in the morning because the Spark streaming job is going haywire. Problem with the Spark streaming jobs is that we all become DevOps after a while. Those runs for a long time. Relaunching the Spark streaming job is a huge endeavor, and you tend to be there babysitting it whether you want it or not. Spark can be something that you launch and then you get the results the next day. Okay, fair enough, fine. Spark streaming functions kind of like a website. When it's down, you're being called.
Okay, let's thanks again our speaker.